Alright, so in this video we're going to be continuing our coverage of Newton's laws, specifically now looking at how to use Newton's laws to solve many of the physics problems we're going to be looking at in this course. And so we're going to follow a sort of multi-step process to solve all these problems, the first step of which is always to draw a free body diagram. And now a free body diagram, which I'll draw shortly, basically illustrates the forces. So it's the forces sort of drawn out. So, for example, if we look at this block of mass m, we have over here on the left being pulled by this tension force from the rope. We can draw all the forces acting on it. So, the first force that will always be there, well, not always, but for the most part in this course we're always going to have gravity, which we'll illustrate as mg, and then because there's no acceleration in the y direction, we know that there's a normal force because it's being supported by this table or floor or what have you down here. Then there's obviously the tension pulling straight to the right, and depending on whether or not there's friction, you may have to draw in a frictional force over here. So here we have drawn all the forces that are affecting this object in this problem. The next step we have to follow is picking a coordinate system. So you can really pick a arbitrary coordinate system oriented any way. So for example, you could have your x-axis going like this and your y-axis going like this, or your x going like so and your y going perpendicular to that like so. But really what we want to do, this should be noted that picking your coordinate system is about being efficient and keeping things simple. So if a lot of the forces are at right angles to one another, you may want to pick the coordinate system that lines up with the forces. In this case we'd use this purple coordinate system, because then you don't have to deal with these various angles that the forces correspond to relative to the coordinate system. Likewise, you also have to pick an origin. And it's always easiest to pick the origin at sort of the starting point of where something is. So this would be, x equals 0 and y equals 0. And that also entails picking which direction will be positive. So if you have, say, a falling ball, you have to decide whether you want gravity to be negative acceleration. In other words, this direction is positive, so gravity is really negative 9.81 meters per second, or if you want it to be positive, basically. So if you have positive g, then this direction down here would be positive. Realistically, you can pick any sort of origin and positive orientation that you want, but the trick is to be consistent. So if g is negative, you have to make g negative throughout your entire problem in all of your equations, otherwise you will mess up your eventual results. Now the last thing you want to do is basically break up forces, accelerations, any sort of vector into its coordinate components. So you want to do the sum of the forces in the x direction as well as the sum of the forces in the y direction. Don't operate in complete vector form. Break the vectors up into their components before trying to solve the problem. So, for example, if you were to look at this block right here, you would break up the total forces acting on the block into the x and y directions. So in this case you have friction and tension acting in the x direction, so the sum of the forces in the x would be tension minus friction, because it's acting opposite the tension. Oppositely, the normal and weight forces act in the y direction. So you would write the sum of the forces in the y direction is the normal force minus the weight. Now just as some sort of miscellaneous notes, something said to be in static equilibrium, that is the sum of the forces acting on it, are 0, only if both the sum of the forces in the x direction is 0 and the sum of the forces in the y direction are 0. As well, the centripetal force, which I'll represent as F centripetal, is not an actual force in physics per se. This has to be created by another actor. So, a string pulling a ball in a circle, or gravity pulling a planet around in a circle. etc. In other words, the centripetal force is just what we refer to as a general term for any force pulling an object to act in a circle. So now, because this is all about using Newton's laws, we're going to be doing some sample problems. So, in the case right here, we have a block suspended from a wall and a ceiling via two ropes labeled T1 and T2, and T2 is acting at some angle theta, so this rope isn't acting straight up and down like that. And our objective is basically to figure out T1 and T2, the strength of those forces, in terms of the mass and the angle, as well as universal constants, which that usually entails g. So we have to look at this situation and sort of assess it. Is the block accelerating at all? Well, no, it's absolutely stationary. It's just staying in that one place. So that means that we have a static equilibrium problem. The acceleration is 0, which means that the sum of all the force vectors is also 0. And this gives us a pretty simple problem from here. Basically what we can do is start off by drawing our free body diagram, first of all. Now, the most obvious force is obviously going to be gravity, and then you have this T1 right here, and T2 pulling off at some angle theta from the horizontal. And so now we have to break up these forces into their individual components. In this case, T2 has a horizontal component and a vertical component given by T2 cosine theta and T2 sine of theta. And T1 acts along solely the x-axis, and mg acts along solely the y-axis. So those are already broken up into their components. Now from there, all we have to do is sum the forces in the x direction, sum the forces in the y direction. So acting in the x direction are T1 minus T2 cosine theta. So in this case, the positive direction is going that way. It's just arbitrary, whichever force you make positive. In this case, because there's an opposite arrow, you have to make the other one go negative. And the forces acting in the y direction, we have T2 sine of theta. Ooh, sine of theta, there we go, minus the weight. So in this case, our orientation we have up is positive. Now, because it's not accelerating, we know that the MA is 0, which means that both of these terms come out to equal 0, or T1 equals T2 cosine theta. And because we don't have a T1 and a T2 in here, we can solve for T2 in terms of just the universal constants theta, m, and g. So in this case, T2 equals moving the mg over via addition and dividing through by sine of theta. We get T2 equals mg over sine of theta. And then because T1 equals T2 times cosine theta, we get that T1 equals mg cosine theta over sine of theta. But from trig, we know that cosine theta over sine theta is cotangent theta, so this becomes mg cotangent theta. And that's how you solve a static equilibrium problem.